I don't hear anything. Justin, do you hear anything?
What exactly you're tested on. So you.
Okay, let's start it again. Yeah.
Hello. As has probably been introduced, my name is Monica, and this is my honors presentation on memes and math instruction. Alrighty, to start us off, I want to ask everyone in the audience to imagine you're a student listening to a lecture that you'll soon be tested on, and this bar is your working memory capacity or cognitive load. The professor is filling your brain with all the relevant information for you to pass this exam, and to keep your attention, they throw in some pretty interesting but entirely irrelevant information. You're actually unsure what exactly you'll be tested on, so you try to remember those extra details plus the rest of the main takeaways. This causes your memory to overload. You end up not doing too well on the exam because you were holding on to unnecessary or extraneous information. Well, in the realm of educational psychology, those interesting but irrelevant tidbits are called seductive details. And the debate on seductive details and their effect is actually still ongoing. Many studies have shown that including seductive details to motivate learning can lower student performance, which has led many instructors to remove these interesting tidbits from their lessons. But some recent studies, such as one conducted in the classroom and not just the lab, suggest that seductive details might not actually affect students' performance at all. A 2020 meta-analysis, or paper that examines trends and themes across multiple other papers on this topic, found that including seductive details for math or statistics lessons in particular might even boost performance. However, the amount of studies that feature math is actually quite limited, making up only 2 of the studies in that meta-analysis. So there's definitely still room to examine whether seductive details are actually helpful for math learning. One common criticism with seductive details research is that there are so many different stimuli that what is considered interesting is often rather subjective. That is why, for this study, I choose to focus on memes, a stimuli that has grown increasingly popular in this age of social media. Memes essentially are just funny content that gains popularity by being shared online, changing as different people make edits and share their own version. A 2020 survey on engineering education has found that undergraduate students in particular were very open and keen on including memes into their engineering lessons. And in another 2020 paper, researchers who observed social media groups that only shared memes about math found that math memes can be broken down into 2 main types: emotional memes and mathematical memes. Emotional memes humorously emphasize subjective feelings surrounding math and therefore tend to generate a lot of reactions. For example, when you see this meme of a person who is so ready to tack on that plus C to the end of an indefinite integral solving process, you might react with a like. Or if you're like me, a laugh emoji because of how accurate this person's face is in reflecting the proud frustration of finally remembering to put plus C after getting so many times. Point is, these emotional memes emphasize relatable experiences, feelings, or mindsets about math. On the other hand is the mathematical meme, which aside from just generating reactions, also invites discussion. These memes humorously combine a recognizable template with a statement about a math concept you can prove or disprove. Take, for example, this meme. Notice the weird orientation. The caption says, "Me and the boys multiplying by I." If you didn't automatically get this, you could imagine commenting, "Why is it uploaded funny?" Which might then start a discussion explaining that this meme, which uses a typically horizontal "me and the boys" template, represents what happens when you multiply by the imaginary number I on the complex plane. You get a rotation by 90 degrees. This is a provable math statement. Because "me and the boys" memes are meant to convey a group of rascals being up to no good, when they mess with multiplication by the number I, they accidentally flip their world over. This way, mathematical memes are like jokes you can only truly understand if you know math, which might motivate people to want to learn math to understand these means. Mathematical means can therefore both be interesting and relevant, while emotional means would be irrelevant to any given lesson, making it a subjective detail when included in the math lesson. Now that we know what subjective details and math memes are, here's the question. What is the effect of math memes on students' perceived cognitive load, performance, and perceived motivation to learn math? Well, given the differences in the way mathematical memes motivate math learning online, and given the past literature that supports how irrelevant stimuli like emotional memes might negatively impact performance, we hypothesized that mathematical memes would help and emotional memes would hurt math learning. To test this hypothesis, we conducted a between subjects experiment with 404 undergraduate students who participated via the online SONA platform, primarily consisting of psychology, linguistics, and cognitive science students. Most of the participants were female, and while age was not collected, many of them were third years and under and had taken at least Calculus 2, which is integrals calculus. And since research shows that math attitudes can often affect learning, we also asked students about their calculus inclinations and found that most of our participants tended to hate or dislike the subject. Now that we know a bit about our participants, how did we test them? Well, we divided them into 3 random groups. All participants from each group take the same pretest to gauge their competency with basic calculus concepts that are shown in the lesson. After the pretest, each group of students watched the same video lesson about a math concept called the pi function. However, at the start of each lesson, each group sees one of 3 conditions. Group 1 sees an emotional meme about how it's better to learn math to understand memes instead of the laws of the universe. This emotional meme is like starting off the lesson with a cheeky but irrelevant joke that induces positive feelings and encourages students to pay attention. Group 2 sees a mathematical meme that uses the you versus the guy she told you not to worry about template and directly involves the comparison between the pi function and the regular factorial discussed in the lesson. Group 3 sees the control stimulus, which is just the title of the lesson. This simple title is meant to represent a typical math lesson that starts without any eye-catching information at the beginning. After watching that lesson, all subjects are asked to rate on a scale from 0 to 10 how much they agree with statements about their cognitive load, such as the instructions and or explanations were very unclear. These were adapted from existing ways of measuring perceived cognitive load in education psychology. Then, participants rated questions about their perceived motivation using that same 0 to 10 scale. Typically, motivation is reported only as an aggregate in subjective success research, but we broke it down into 3 different subtypes to gauge motivation that might have occurred at different stages of the lesson. To measure intrigue or motivation about the start of the lesson, we asked participants to rate how intrigued they were or how much they wanted to understand the rest of the lesson after seeing the meme or title at the beginning. To measure motivation during the lesson, we asked about students' enjoyment of the lesson and how much attention they paid throughout. And to measure future motivation, we asked how much students generally appreciated math or would look for similarly structured lessons in the future. These specific questions were also adapted from existing assessments of perceived motivation. After finishing those self-ratings, participants are then tested on the material. The post-test uses both retention questions such as, what is the name of this function, which are pulled straight from the lesson, as well as multiple choice transfer questions such as this one that require them to apply what they learned. After we collected all this data, how did we analyze them? Great question. We used what is called linear regression analysis to find any significant correlations. A simplified version of this type of analysis reads like this. The dependent variable, which means perceived cognitive load, performance scores, or perceived motivation, is modeled by the intercept, which is the mean value for this dependent variable when all other predictors are 0, plus the covariates, which are pretest, calculus inclination, calculus level, and gender. We include these covariates into the equation because things like pretest scores, for example, can often largely explain how a dependent variable like performance might vary. And we want to just be aware of these effects so that when we add in the condition to the equation, we can say whether the control or mathematical or emotional mean conditions do significantly correlate with our dependent variable, even when we've accounted for different calculus levels or different inclinations, etc. All right, so what did we find? First off, how well did the participants do on post-tests? Well, not too well, it seems. Participants averaged only about 2.7 points out of 7, or 39% on post-test. Furthermore, we found no significant correlation between each of the mean conditions on perceived cognitive load or performance. If we take a look at this chart, we can see that only the covariates were good predictors of cognitive load or performance, and there were no significant coefficients for either of the mean conditions. As for motivation, while there were no effects of either mean on aggregate lesson or future motivation, there was, however, a significant positive correlation between intrigue and the mathematical mean. This means that compared to the control condition, students that saw the mathematical mean at the beginning were about 1.1 points more likely to want to understand the rest of the lesson. This correlation was still significant, even after we did a multiple comparisons correction to account for the fact that we had re-examined motivation multiple times when we broke it down into its subtypes. Another interesting thing to note is that unlike with the other motivation types, pretest scores was not significant for intrigue, suggesting that students, regardless of calculus skill, can still find themselves curious about the lesson after seeing the mathematical mean. But what do these results tell us about the seductive details effect? Do interesting but irrelevant stimuli lower performance like much of the literature suggests? Nope, they do not. Neither of the means significantly affected performance. The mathematical mean, despite being relevant, did not help, and the emotional mean, despite being irrelevant, did not hurt performance or induce more perceived extraneous load. Even when considering the specific math context, there was no significant boost in performance for the emotional mean condition either. This would add to the side of the seductive details debate that finds no detectable harmful effects of including interestingly irrelevant stimuli into a lesson. That said, there are many limitations with this study, including the fact that we weren't able to get data on whether specific participants understood the mean. And while we did verify that participants rated the mathematical mean as both relevant and interesting, and the emotional as only interesting but not relevant, we were unable to see whether they believed the mean was funny. Another limitation is that this was only a one-shot math lesson. Math often takes so much longer than just a 12-minute video to absorb, which is probably why performance scores ended up being so low, which is related to another limitation with running the study on SONA. That is, using multiple choice questions aren't the best way to test math learning. Furthermore, each of the stimuli only appear very briefly, about 30 seconds at the beginning of the 12-minute video. This brevity might have made any potential effects of the stimuli to stay under the radar. And lastly, this meme only uses 2 math memes in relation to one math concept. There is lots of room to explore a wider variety of math memes and see whether their effect is actually generalizable. With these limitations in mind, here are the main takeaways. 1. The emotional mean, despite being an irrelevant seductive detail, did not significantly hurt learning. 2. The mathematical mean was able to make students more curious about math, despite appearing only so briefly, and that this curiosity effect was not affected by students' existing calculus competence. 3. There is so much room for further investigation into math means. If showing the math mean so briefly at the beginning can still produce an effect, it would be interesting to see if interspersing the mean would keep up perceived motivation throughout the lesson. And if this were more than a one-shot lesson, it would be interesting to observe whether intriguing memes embedded into a math series could have long-term effects on students' performance and attitudes about math. And with that, references, yes. I would like to thank my committee members, all the participants, and all of my friends and colleagues. As a token of my appreciation, here are some of the beautiful math memes people have sent over after I told them about this project. And with that, please feel free to ask any questions you might have. Thank you.
All right. Thank you, Monica.